So now remember, you start off with what did we learn about this? We learned that you've got enthalpy of formation where elements they turn into, and remember, lattice energy is for ionic compounds only. So what you did was that you've got enthalpy of formation where elements turn into an ionic solid, and the process of turning it into an ionic solid is that you atomize it first, you break the bonds in the elements, and then you ionize them, and then you form the lattice, right? So that's your lattice energy. So this is basically the more detailed version of the Born-Haber cycle. So over here, they've actually made the more detailed version, and they're asking you to label this. So what do you think 4 is? Was there any idea what 4 is?
No, I'm not sure.
It's elements turning into an ionic solid. What is that? One mole of a substance getting formed from its elements. This one is delta
Is
HF.
it oh yeah.
Okay. As now they've given you enthalpy of atomization of sodium. So what happens in atomization? In atomization, 1 mole of an element, not 1 mole of an element turns into 1 mole of gaseous atoms, right? So what is A then? Like they're atomizing sodium. So what is A?
Is it enthalpy change of atomization?
But what's A then? What would you write? Like it's atomization of sodium, right? So sodium element turning into what?
Na gas.
Okay, so it's going to be Na gas, right? And it's 2 moles, right? Because there were 2 moles over here. It's 2 times the enthalpy of atomization of Na. What do you think 1 is? Like what happened over here when you went from this point? Like ignore A now. What do you think happened in 1?
Is it the enthalpy change of atomization of oxygen?
Like, did anything happen to oxygen? Like there's half O2 gas, there's still half O2 gas. It's got nothing to do with oxygen because nothing happened to oxygen. So what actually happened in what does this arrow represent?
Sodium was ionized.
Because that's the first ionization energy of Na and times 2 because there are 2 sodiums, right? So now oxygen is getting atomized, enthalpy change of atomization. So what is B?
Is it O2 minus?
What happens in atomization? In atomization, what happens is in atomization, what happens is electron affinity, bond energy. This was atomization. In atomization, what happened was that 1 mole of atoms gaseous was formed from its element, right? And the element has to be in its standard state. So the element is going to be in its standard state. So if I go back, this is enthalpy change of atomization of oxygen. So I'm going to get 1 mole of oxygen gaseous atoms over here. Is that clear? You get from its elements. Like I I had a half O2, now I've got 1 mole of oxygen gaseous atoms out of it. Is this clear?
Yep.
So what do you think 2 is? Like what happened when you go from this to this point?
Is it the oxygen's gaining 2 electrons?
So what is that called?
Is it electron affinity?
Yeah, that's electron affinity. That's the first and second electron affinity, or referred to as electron affinity of oxygen. That's the first one, and electron affinity of oxygen -1. So, anyways, you've got gaseous ions. Now they're turning into sodium oxide. So, what is 3?
The lattice energy?
That's your so that's your lattice energy. So you've got your Hess cycle complete. It's basically you had your enthalpy change of formation. So the elements were atomized. I think. I mean, they kind of mixed it up, but uh, they were atomized and they were ionized, right? I mean, they did the sodium part first. They atomized sodium, and then they turned it into ions. Then they did the oxygen part later. They atomized oxygen, and then they turned it into ions, right? And then the ions they formed the lattice. So basically, this is all about that. Now, if they've given us values for enthalpy change of atomization of sodium, that's 107. So this value over here is, I mean, this arrow over here is 107, and it's going to be times 2. What else? The other one is they've given us the first electron affinity and the second electron affinity of oxygen, which is -141 plus 798. So this part over here is -141 and also plus 798. I said then you've got what else have they given us? They've given us the enthalpy change of formation of sodium oxide, which is -414. So this one is -414, and they've told us that the atomization of oxygen is basically equal to the half the bond energy of oxygen. So that is half the bond energy of oxygen. That is 496. Okay, that's going to be given in the question over here. It's in the data booklet. So that's half into 496. I mean, it's this part. Finally, you're left with the lattice energy. They're asking us to calculate the lattice energy. So, and what we also need is the ionization energy of sodium. So that can be obtained from our data booklet. Just a second. So sodium's 494. That's over here. So this one is 494 times 2. So the only thing that's left is to calculate the lattice energy. So what is the rule that one path is equal to the other path? So here's your one path, and that's your, I mean, this side over here, that's your other path. So you can just equate them, and that's so basically this arrow goes in the opposite direction. So your lattice energy would be equal to plus 141 and minus 788. Do you have a calculator with you?
Yep.
This one goes in the opposite direction, so it's going to be minus half times 496. This also goes in the opposite direction, so that's minus 494 times 2. This one backward, so that's minus 107 times 2. The last one is in the same direction, so that's minus 414.
So that's all equal to the lattice energy.
Yes. According to Hess law, it's one path is equal to the other path. So what do we get?
I got -2521.
You're getting -2521, which is probably going to be right. One of the worksheets I sent you that has copy written in it, that's the solved version. So let me just double check. It was this one. So so this one hasn't gotten are you sure -2521?
No, I'm not sure, but that's what I got.
See, I mean, this is kind of the same thing. It's the only thing is that when you're solving these questions, you have to be very careful with your calculator. It's just make sure that you haven't made any mistakes. -2521 looks all right. Because lattice energy usually is exothermic, and it's around. It depends on the strength of the lattice. Which I told you that it depends on the charge of the ions. The stronger the charge and the smaller the ions, the more attraction they're going to have. But anyway, so that's -2521. That kind of looks all right. And usually it's in that range. If it's a weak lattice, it's going to be closer to 1,000, -1,000. If it's a very strong lattice, it would be around -4,000. The next one. So the next one is it's the same. It's the same exact question. We can do this part. How would you expect the magnitude of the lattice energy of magnesium oxide to compared with? So magnesium oxide with comparison with sodium oxide. Who's got the stronger lattice?
Is it magnesium
And why?
oxide? Because it has a higher charge.
Okay, so it's got the higher charge. Magnesium has the higher charge. And so magnesium has the higher charge. Is it smaller as well or not?
It's not smaller.
Why is it not smaller? Like magnesium has a proton number of 12. Sodium has a proton number of 11. They both have exactly the same electrons. Magnesium ions have 10 electrons, and sodium also has the ion has 10 electrons. So who's going to attract its electrons strongly? I mean, it's going to be magnesium, right? 12 proton.
Magnesium.
So not only does it have it's got a greater charge, but and it's got a smaller ionic radius. So because of both these factors, it's significantly stronger. Like if you look at the melting points of if I search for the melting points of sodium oxide, then it's probably close to 1,000. Yeah, 1.13. And if I look for just a second, similarly, if I look for magnesium oxide, it's probably going to be close to 3,000. As the next one, do you know any uses of magnesium oxide?
Is one like as medicine for stomach acid, digestive issues.
Yeah, I don't think magnesium oxide is used for that. I mean, the most.
Oh,
No, I don't think. I mean, it could obviously neutralize. You've got calcium, like you've got carbonates which can do that. Like a lot of things have carbonates in them. So what's magnesium oxide is used for is it's I'm going to write down this over here. Okay, we did talk about lattice strength. Just a second. Okay, so lattice. So this is where did we? This is where we talked about how to determine the relative size of ions, lattice energy for stronger lattices, right? I mean this part. So I'm going to talk about strong, like really strong lattices. These are known as ceramics, and they tend to be ceramics are substances that are. I mean, ceramics could be any substance basically that is strong, durable, high melting and boiling points. They are very good insulators. Like even the thing with insulators is that even substances that are non-conducting or they tend to burn or they tend to like if the current is very high, like even trees catch fire when the current is really high. Branches can sort of burn and they can break down. I mean, the structure would break down. So ceramics are like really strong substances because the ions are so strongly attracted to each other that nothing happens to them. Okay? No matter how high the temperature is, no matter how strong the electric current is, nothing really happens to them. So they're really strong. They're structurally very strong as well. So some common ceramics, you need ceramics because you've got but the reason you need ceramics is for high voltage transmission. Like, you must have seen wires which like high voltage transmission wires are never covered with I mean they're not coated with plastics or anything because they're going to I mean structurally it's impossible that anything could survive high voltage transmission. So the things that are holding the wires, the connectors, etc., they have to be something that's like very very strong. So it's high voltage transmission, furnaces, ovens, heat shields. Like if you're for spaceships, etc. So magnesium oxide is one of those substances. Like it's very strong. Even your ovens are made out of magnesium oxide. You've got ceramic baking trays, like you see them in supermarkets. I mean, you see the cheap ones. The cheap ones are made out of metal, usually steel or aluminium. The more better quality ones are made from ceramics. Aluminium oxide is a good ceramic. Okay, that's also very, very strong. A lot of your high voltage transmission equipment, like your transformers, etc., they're made out of aluminum oxide. There's one other ceramic substance as well, which is not an ionic compound. It's actually a covalent compound. That's silicon oxide. I mean, you make houses out of bricks. You make ovens out of clay. The reason because sand is kind of like really tough as well. But that's a covalent example. But is this idea clear that but not all ionic compounds are like really really strong. I mean the ones that have lower charges they're not that strong. Like NaCl is not really that strong. NaCl has a melting point like your normal table salt. You can crush it with your hands. ठीक है Varda, is this clear?
yeah.
So magnesium oxide would be furnaces and heat shields, etc. Like your like the space shuttle has this black underbelly that is covered with tiles that are made out of magnesium oxide. So now this one, calcium metal reacts with chlorine, so you have to draw the Born-Haber cycle. So what are you going to do? You're going to atomize it. Okay, so I'm going to just do it in one step. So I'm going to atomize calcium solid to calcium gas. And the same step, I'm going to atomize the Cl as well. I'm going to turn it into Cl gaseous atoms. So this is the enthalpy change of atomization of chlorine, but that's times 2. And it's also the enthalpy change of atomization of calcium. Then I'm going to ionize them, and I'm going to do that in one step as well, just to save time. So calcium turns into ions, becomes gaseous, and the two Cl atoms, they also turn into gaseous ions. Now this one is equal to what? It's equal to the first plus second ionization energy of calcium. And for Cl, it's the electron affinity of Cl and times 2. And once I've got gaseous ions, I just need to make a lattice. So that's it. So that's my lattice energy. Well, is this clear?
Yep.
So again, all you have to do is they've given you some of the values. So the values that are given are what? The enthalpy of formation is given, that's minus 796, so that's this part. Atomization of calcium is given, this one, it's 178. So that's 178. Just a second. As the next thing that's given is electron affinity of chlorine atoms, that's minus 349. Times 2. The first, sorry, so the first and second ionization energy of, just hold on a second. So then you've got the first and second ionization energy of calcium, which can be obtained from the table over here, which is so which one is, just a second, my it's better. Use calcium is over here. So where's calcium? Calcium is 590 and 1150. So where's the first? This one is 590 plus 1150. So now can you calculate the lattice energy? One path is equal to the other path. So basically your lattice energy is equal to all of this stuff, which is the first arrow has to go backwards. So that's 349 times 2 minus 590. That's so the sign's invert, minus 1150 And the enthalpy of atomization of calcium also reverses, that's minus 178. We need the atomization of chlorine atoms. This is not given. So this is basically what you're doing is you're breaking a Cl-Cl bond when you're atomizing it. Like if you've got chlorine gas and it turns into two Cl gaseous atoms, so you've basically just broken one Cl bond, which is also given over here somewhere in the data booklet. That's so the Cl-Cl over here is given as, it's given over here as 242. So the Cl-Cl, this one over here is given as 242. That's so that's going to become negative as well. And then you've got enthalpy of formation, which is minus 796. So that's your lattice energy. Is this clear?
Yep.
What's the answer?
Minus 2258.
This one is minus 22. So the next one. So this one, can you draw the bond? I'm going to write down the missing values. Can you draw the Born-Haber cycle? He says, write the equation, the following data. Construct an energy cycle, a value for the lattice energy of MgCl. Now, one thing, just remember one thing, that's here Mg is +1. So the ionic lattice only has Mg +1. So you don't turn it into Mg +2. So they're looking for this value, but you would have to construct the whole Born-Haber cycle. I'm going to give you the Cl-Cl bond energy, which is 242. What else do you need? You need the magnesium ionization energy. So the first plus second ionization energy of magnesium, that's where's the first plus second? That's 736 and 1450. We don't actually need the second one because Mg is only turning into Mg +1. I guess that's about it. Electron affinity of Cl is already given. So as I said, we construct the Born-Haber cycle and tell me what the answer is. Okay, do this yourself.